Okay, hi everybody, welcome back. This is the continuation of the second video of the 10th week when we are discussing alternative approaches or algorithms for detecting groups of nodes in a network. We already talked about approaches called block modeling, and in this video we will also introduce the stochastic block models and also some other types of stochastic models. As you will see, stochastic block models, or SBMs, how we usually abbreviate them, are not by itself an approach for detecting groups in a network, not an algorithm for detecting groups in a network, but are actually a model of networks that you can also use for detecting groups. So turning the things the other way around. So let us move to the slides. So we already, within the course, we already introduced a couple of network models. So if you remember first the Erdos-Renyi random graphs, or simply random graph model, where we can specify the number of nodes and also the number of links in a network, or a probability that there should be a link between a pair of nodes. Then we went on and introduced so-called configuration model, that where we didn't only set the number of nodes and the number of links, but also the exact degrees of the nodes in this random graph. We could also go on and introduce something called exponential graph models, or sometimes denoted P-star models, where you can set the number of nodes and also any other expectations that you would like your network to have. So for instance, you could specify the number of links and maybe the number of connected triplets and the probability that the connected triplet forms a triangle, and so on and so forth. And you can read more about this in the Newman's book. You will also see there that it turns out that although this is like an most ad hoc generalization of the models that we have seen so far, it turns out that it simply doesn't work. And you can read about that in the Newman's book. In this video, we will first talk about the model that is called stochastic block model, where you don't only specify the number of nodes, but you also specify the partition of these nodes into some groups or clusters, here denoted with large C, and the probabilities of links within clusters, between clusters, and so on. And later on, we will also just briefly mention something called the hierarchical model, which is based on the same principles as the stochastic block models, and it was introduced in 2008. So let us first talk about stochastic block models. How these are defined? As you will see, this is a simple generalization of an Erdos-Renyi graph to groups. So imagine that our model is specified as follows. First, we have a group of nodes, say 10 nodes for instance, and we have another group of nodes of, say, let's say 5 nodes, and also a third group of nodes. And assume that the first 10 nodes go into this group, the next 5 nodes go into that group, and so on. Then what we also specify is the probabilities of links, for instance, within the groups. So let P sub 1 denote the probability of a link between two nodes that are both in the first group. P sub 2, probability of two nodes that are in the second group, and similarly P sub 3. Now what we are left is also to define the probabilities of links between the nodes that are in different groups, and I will denote them with P sub 1, 2, P sub 2, 3, and P sub 1, 3, as you can see on the blackboard. And this is basically our model. So once you have specified which node goes into first, second, and third group, then you can simply use this probabilities and based on that generate a random graph with that kind of group structure. And you can imagine that if we set these inner probabilities to be something very high and these between group probabilities to be something relatively low, then you would probably you will get a graph with some community structure with 3 communities. For instance, we could also specify that this probability is high and this probability is high and all the other probabilities are low. What we will then get is one community and a roughly bipartite structure between the second and the third group, and so on. So this is how the stochastic block models are defined. And as I said before, each of the groups are basically their own Erdos-Renyi graph model with some specified probability, and you also have the links between the groups. So let's look at some formulas. So in a stochastic block model, we define the division of the nodes into groups, here denoted by C, and the probabilities of links within the groups and between the groups. And for each link, then the link is placed between nodes I and J with some specified probability that depends in which groups these nodes I and J go. So let's say that C sub I here denotes the group label of the ith node, and C sub j denotes the group label of the jth node, then this probability will be exactly one of the probabilities that I have shown on the blackboard. Now, imagine that you are given one particular graph and these clusters and probabilities P. What is the probability that under the model with these groups and these probabilities P, you will actually observe the graph that you are looking at? This is denoted here with graph G. So what I can do, I can take the product through all possible pairs of nodes I and J, and if the I and J are actually connected in our graph, this A sub ij, which is an element of the adjacency matrix, will be 1. And so we will multiply here with the probability corresponding to those pairs of nodes I and J. And so in the case when I and J are connected, I'm taking the first term. And in the case when I and J are not connected, this second power here will be 1. And what is the probability that nodes I and J will not connect is simply 1 minus the probability that nodes I and J will connect. And this is the basic formula that we get. You can also write the formula not over all pairs of nodes, but over all pairs of groups or clusters. And you come up with this formula, and here are some new terms. Small n with the subscripts that corresponds to group labels is basically the number of links between groups I and J, and let large M denote the maximum possible value of small n, which will be basically the product of the sizes of the groups where I and J are, if these two groups are different. So this is this n sub I and n sub j, and otherwise if nodes I and j are in the same group, then the maximum will be n sub I over 2, obviously. So we have written down the probability that we will, under this specification of clusters and probabilities, that we will observe this particular graph G that we get. Now, to move on, it turns out that the maximum, you can easily see that the maximum likelihood estimates of these probabilities P's are simply the densities of the clusters or the density of the links between the clusters in a network that we actually observe. So the maximum likelihood estimate for P between the groups C sub I and C sub J is simply the density between those groups or within that group, if that is the same. So we can plug these P's then into our formula, and we get the probability that we will observe G given our clusters. And now notice that this is not conditioned on P because we take the maximum likelihood estimates. And further on, when you do some maximum likelihood estimation, usually we don't work with the product of probabilities, so to compute the likelihood, but we usually take the so-called log likelihood, so taking the logarithm of this formula, so that instead that we multiply some usually very small probabilities that could be numerically unstable. We rather sum the values, so under the product, under the logarithm, the product becomes a sum. And since the logarithm is a monotonically increasing function, the maximum will be at the same place. And this here at the bottom is the final formula that we get. So we get the log likelihood of particular network or graph that we observe, given some partitioning in two groups. So how then now to use this in some log algorithm? You could try different partitioning into groups. For each, compute this log likelihood and take and say that the right partitioning into groups is the one that gives the highest log likelihood. So in other words, the most reasonable partition into groups is that one that generates our graph G with the highest probability. That is, that for that partitioning, our model, our graph is most likely to occur. And this is basically how stochastic block models work. You can use, again, some, say, relocation algorithm or some greedy optimization, where you move the nodes between the some predefined number of sizes, and you try to optimize the log likelihood. And approaches for that are implemented, for instance, in the graph tool library by the author is Tiago Peixoto, which is at this point probably the most well-known author in community detection, network clustering, stochastic block modeling, and so on. So if these are the approaches that you would like to use, for instance, for your course project, maybe use his implementations, because it turns out that the algorithms and implementations are rather involved in so not to so that you're not having problems with, for instance, resolution limit, that the things convert relatively quickly, and so on. And this, what I have just explained to you, is basically stochastic block models. And you can not only use them for detecting communities, you could also use them to generate some random graphs with some predefined group structure. These are basically stochastic block models. Okay, at the beginning, I also mentioned that I will briefly introduce so-called hierarchical models introduced in 2008, where the idea is basically the same as for stochastic block models. The only reason is that you don't specify the division into groups, so these C parameters, C clusters that we had, but you specify the entire hierarchy of groups, like shown here at the bottom right. And then here, if I zoom in, at the very bottom, you have individual nodes in a network that are then connected in some hierarchy that you want to infer within your algorithm. And the inner nodes in this hierarchy have some probabilities assigned to them. And in order to figure out what is the probability of a link between two particular nodes, I and j, so for instance, this leftmost node here, and for instance, this purple node here, you go up to the hierarchy to find the lowest common root of these two nodes. And the probability assigned to that root is basically the probability of a link between nodes I and j. So now we can write down the formulas exactly as we did before. So let's R sub ij denote the lowest common root of node I and j. This is basically the probability of a link between node I and j. And for each root, it has two, it's a binary tree, it has two subtrees, left subtree and the right subtree. And their sizes are simply, the product of their sizes will be simply the maximum number of links that can appear between the subtrees L and R as before. And then we write down the basic formula for the probability that with this hierarchy and these probabilities, we will observe one particular graph that we are dealing with. Again, you can write this product over the roots instead of over pairs of nodes. And again, as before, turns out that the maximum likelihood estimation for these probabilities is simply the density. So at the end, as before, we simply get the log likelihood. Now, the only thing that you are left with in order to use this approach is to find some reasonable algorithm, which can be just some greedy local optimization that optimizes this likelihood, that finds the hierarchy that is most likely to generate the network that we have. And this is basically it regarding the hierarchical stochastic models. We are left with one single slide that is basically summarizes some of the approaches that were proposed in the literature. At the very left, we have this idea of stochastic block models, and this matrix, and on the left side is basically showing you the probabilities within the groups and between the groups, and based on that you can generate a graph. If you and then use an algorithm that infers group structure or clusters that are most likely to generate your network. If we would apply that kind of approach, just a second, to Zachary Karate Club network, as you can see here, that have some non-sociological division into two groups, what will the algorithm do is, and you specify that the number of groups should be 2, what will the algorithm do is it will push high degree nodes into one group and all the rest of the nodes in the other group. Because in that case, you are most likely to generate the observed network. And this is a completely reasonable division. This division is actually called core periphery structure. So you have a core of nodes, and dense central core of nodes surrounded by some sparser periphery. These are structures that we will discuss in the next video. But the reason why the network is not divided into two communities, for instance, is due to the fact that the degrees of the nodes are so different. So for that reason, people also came up with something called degree-corrected block models that will take into account also the degrees of the nodes, and in that case, it will divide the network into two communities. Notice that both of the divisions are reasonable. Based on maximum likelihood, the core periphery structure gives you higher likelihood that the division into two communities, but in practice, um, you would have to decide whether to use the degree corrected block model or the classical block models. And usually a good rule of thumb would be if the degrees of the nodes of your network are considerably different between one another. So for instance, you have a large scale free network with a power law degree distribution. Usually you get a better division with the degree corrected model. I also mentioned that the Peixoto is the main author of these approaches nowadays, and he basically defined some principled approaches how to infer group structure based on block modeling or block models, and he usually infers the structure in a hierarchical manner, as you can see in this figure here. If we move on, why is this working so slow? We also mentioned some hierarchical models that infer the entire hierarchy of the network, and then you can cut that hierarchy at some level to get some desirable number of groups. And I only want to mention two other terms. One is called role models, and the other is called image graph, which is basically the same idea as the stochastic block models, although the terminology is a bit different and the algorithms are a bit different. So if you will find these terms in the literature, you know that, what they are referring to. And this is basically the last slide. So in summary, what you should remember is that stochastic block models or block modeling are approaches to detect general groups of nodes in networks, regardless of what kind of groups these actually are. Are these communities, bipartite structure, cooperative structures, or anything like that? And for instance, stochastic block model will find the group structure that is most reasonable given your network. This might be, for instance, community structure, or it might be something else. And something else, for instance, could be core periphery structure that we will discuss in the next video. So this is it for this video. Thank you for listening, and see you in the next video.